Good morning, everyone. Like Dr. Kolbeck said, I'm Joy Sandman. I'm a fourth-year physical therapy major, and I perform my research under the guidance of Dr. Gifty Blankson and Dr. Thomas Spudich. So I decided to focus on cardiac troponin due to my healthcare-related focus. So when you are testing for the presence of a heart attack or a myocardial infarction in the ER and any kind of healthcare setting, the thing you test for in the blood test is your cardiac troponin levels. So when your heart is damaged, like in a heart attack, troponin is released into the bloodstream, so that's what they're testing for. The problem with this now is currently it's very expensive and takes a longer amount of time. So the average amount of time in a waiting room is about an hour and a half to test for this. So, and about half of that time is just testing, just doing the test like lab process. So reducing the amount of test time and simplifying that process would definitely be a significant improvement in the overall quality of care. Additionally, with the point of care application, the second part of that title there is that you wouldn't necessarily have to go to the emergency room to either further expose yourself, which is especially pertinent now, or just in like rural areas or where medical care is more difficult to access. That having a point of care application would definitely make this testing more accessible, which would also overall improve patient outcomes. So that's where kind of my focus is on this. So I'm going to be presenting my poster that I presented at PitCon, which is an analytical chemistry conference. Dr. Blanks and Dr. Switch and I presented there in March. So I'm going to be presenting this poster as well. But just a little background first. So microfluidics is definitely a major growing field within chemistry. It is kind of the focus of testing and studying controlling fluids at a micro level. So the size of a micron, 10 to the -6 meters and below. So that definitely reduces your overall cost as you're using smaller amounts of your fluids, your samples, tests, things like that. And also the testing equipment can be smaller, more transportable, easier to reproduce. So that lowers your cost, makes it more accessible overall as well. Point of care, like I said, is bringing the either testing or application to the patient rather than bringing them to the resource, which reduces cost and just makes it more accessible to a group of people. So both applications of this testing for troponin levels through a blood test using microfluidics and point of care testing reduces the cost overall and improves patient outcomes. So a little background into our specific test that we're working on. So a lateral flow assay, the most easiest example I can give to you is a pregnancy test, which is a lateral flow assay. So we're using a very similar design to test for troponin. So overall, this is a side view of our test strip. So you can see we do have 4 different kinds of paper here. They're all kind of overlapping on our test strip. Overall, our test strip is about 50 millimeters long, so it's very, very small, and a ½ centimeter wide. So so the fluid moves from left to right. So starting at the sample pad, that's where you add your sample. So you add the blood sample. Currently in our test, we're adding troponin diluted in a special buffer that runs through the test. On the conjugate pad is where we have our conjugate, which is where our gold nanoparticle, which is the color so that we can tag the antibody so we can see the results at the end. Our gold nanoparticle and our antibody are conjugated or bound together, and that's where those are placed. The nitrocellulose pad is where we place our antibodies to see the results at the end, and the absorbent pad is where the collection of the excess sample, so once it all runs through the strip, that's where the excess fluid is collected. So you can see, like I said, this is where, so the troponin is placed on the sample pad. Our conjugated antibodies are located on the conjugate pad. We have 2 types of antibodies. So antibodies bind to a very specific thing called their antigen. And they will only bind to that antigen, which makes them great at detecting things because you know if it binds to your antibody, then you know exactly what you have. So only troponin or CTN1, which is its abbreviation, will bind to the anti-CTN1 antibody. The specific antibody we use to detect the troponin is made from a mouse antibody. So the green antibody is made from goat antibodies, and it detects mouse antibodies. So it just detects any antibodies that run all the way through the test. So once we add troponin to our test strip, the first thing it does is it flows through and it attaches to the conjugate. So then we have the troponin, an anti-CTN1 antibody, and a gold nanoparticle all bound together. As the fluid keeps flowing through the test strip, the first line, so the troponin binds to another anti-CTN1 antibody. So we have a whole stack there. So you can see that the gold nanoparticle is on top, then the antibody, troponin, and then another antibody. The second antibody shows that we would just bind the conjugated antibody to the green anti-mouse antibody. So in reading these test results, so this shows your test line. So we have the first test line shows the detection of troponin, and then the control line just shows that the antibodies made it all the way to the end, so that you know that you had a successful run, so that the test can be used. So at the bottom, it shows your results. So if there are no lines present, then that's an invalid test that can't be used, as you're not sure if the antibodies made it all the way through. Having just one line present means that it is a valid test, as the antibodies made it all the way through, but no troponin was detected. So the test line wouldn't be present, but the control line would be. And then a valid test with troponin detected would have two lines. So the test line would be present because troponin was present, and then the control line would be present because the antibodies made it all the way through the test strip. So going back to my poster here, our methods section just describes each of the processes that we use and all the specifics for going through each of the processes. So one of the aspects that we spent the longest amount of time on was the conjugation of the antibody. Due to there being so many variables and it being such an extensive process, it involves a lot of centrifuging, adding multiple buffers. We added BSA after adding the antibodies. So you add the antibodies, have them bind to the gold nanoparticles. Then after that period, you add BSA or bovine serum albumin to block all the other binding sites, so you know it's only your antibody that's bound to it. After a couple centrifuging steps, removing the supernatant or the excess fluid, and then resuspending in the buffer, that's just to kind of purify the solution more, make sure you know exactly what's in our conjugated antibody. And so after we conjugated it, we had to test it to see if it was detecting the troponin that would flow through and only be detecting the troponin. So if you look at our data section, you can see that we tested a lot of trials of it, but this is one of our final ones. So you can see we had 6 trials, A through F, and we tested multiple antibody sizes, pHs, and different kinds of buffers. We mainly followed Zhu et al. Article that I've cited at the end with their successful run. That's why we chose to use the 15. They were successful with both 15 and 40 nanometers of gold nanoparticle size. And they used 8.5 as their pH. We tested it independently and found that 7.8 was also successful. So that's why we used the 2 different kinds of pH. In the Zhu et al. Article, they had a lot of preservatives added to their buffer to maintain its storage life, be able to use it for a longer period of time. But we were trying to keep our process as simple as possible to remove as many variables as possible. So we tried it with and without the preservatives throughout. So figure 1 shows that our 6 different antibodies, conjugated antibodies. So if it conjugates properly, it will be bound just enough so that the antibodies stick to it, but not too much that they all clump together. So if it turns bluish purple, that means that they all clump together. And a reddish color is your ideal. That means it conjugated appropriately. So you can see from table 2, we compared the amount of red from each of our tests. For image analysis, we used software called ImageJ, which is a free online open source image analysis program. I use the color analysis tool to create histograms and just analyze the amount of red, blue, and green color at each of these areas. So for each of these tests, I analyzed the amount of red. So each of the dark circles shows where our test spot was. And so I analyzed both where the troponin was and just where the antibody had spread out. And so I compared the amount of red to where the antibody was to just the amount of red of the nitrocellulose, found the difference between that, and compared those between when troponin was present and when it was absent, to detect whether the red was coming just from the conjugated antibodies or from it actually being condensed enough to show that troponin was present. So you can see our most successful one was trial A, which is what we expected. That's why we duplicated. A and B are identical. Due to the articles and just our previous success, we expected trial A, that combination, to work the best. So that's how we knew that that was our most successful conjugated antibody. So that's the one we would use for future test strips. Figure 3 just shows that we were measuring the amount of red, green, and blue and comparing them. And figure 4 shows that it was significantly more red on when the antibody was located, like where the troponin was, compared to just the nitrocellulose membrane. Further testing, so we used 2 different kinds of cardiac troponin antibody. We used one from Thermo Fisher and one from Sigma Aldrich, which are just 2 different science production companies. And so for our conjugation, we used the Thermo Fisher antibody. And so we wanted to see if it was better, we got better results if we used the same antibody also on the test line, or whether it would be better to use a different brand of cardiac troponin. So we compared the Thermo Fisher to the Sigma Aldrich. You can see we found a better difference, or a more noticeable difference with the Thermo Fisher. So using the same brand of antibody, we found better, more visible results. So it's likely more beneficial to use the same antibody rather than adding in another variable. But as you can see, we're really just getting started on this research. I've spent about a year on it. Previously, I worked with myoglobin on a similar project, just trying to figure out which of the assays is the best way to detect proteins at a point of care level. I switched to troponin because that is the clinical, like, gold standard for testing for heart attacks. So that's why I made that switch this year. We also have to get it to a level of being able to detect to 1.2 micrograms per liter, which is the clinical standard for detecting a heart attack. So there's definitely lots of future work in this direction, but I'm just super passionate about being able to improve healthcare outcomes in any way possible, definitely getting our patients just the best quality of care. So with that, if there are any questions, and here are my references. Thank you.
Thank you very much, Joy. Can you see the chat?
I can, thank you.
All right. I'll let you just answer questions from the chat, or if people have questions, they're free to ask them.
So Dr. Kolbeck asked what kind of samples would this work on? Primarily this would be a blood test, as the troponin levels are monitored through your blood. So that would be the sample that we would eventually be adding. It's just a sample in the referral system. Good question. Where would we get the samples from? Or who would we get them from? I mean, eventually it would be great to apply for a clinical trial and get them from actual patients to be able to detect baseline levels, or with people who we suspect of a heart attack. So that would be the goal of that eventually. Right now we're just testing with cardiac troponin from like Sigma Aldrich or Thermo Fisher, and diluting it in the same buffer as the conjugated antibody. Budger asks, is it temperature sensitive, or if the sensor is? So currently we are just using image analysis for this. So it is not temperature sensitive. We just use it at room temperature, which is also what the article said. And that would be the goal, is to keep it at room temperature so it's more accessible to patients overall. And image analysis, if we could develop like a certain app or application so that you could just read the test with your iPhone with an app, just using your phone camera, that would make it even more accessible to patients. Has Maryville participated in any studies with actual patients? I know a lot of the physical therapy research has definitely worked with actual patients for sure. I'm not sure if we have worked with any like lab wise, but that's definitely something to look for in the future for sure. Dr. Sangostini says that it's a one-step assay, which makes the clinical application easy, but it seems like it's time dependent. How can time dependency be overcome? That's definitely something we're working on. That's kind of why the one-step assay is so appealing, is because you wouldn't have to wait as long for the reaction. Last year, we worked with paper-based ELISA, which is just another kind of biochem approach for detection of antigens using antibodies. And time dependency was one of the main reasons we switched to a lateral flow assay, is because it's so much faster. And the tests only take about maybe 20 to 30 seconds to run through, like overall a minute maybe. So the tests are very fast once you have the entire strip prepared. Mike asked, would blood need to be spun down to be utilized with this test? Possibly positives. Definitely, we need a lot more research before we get to being able to use real blood for sure. I'm not 100% sure on that, how the blood would need to be prepared for this use in the test. Definitely, the possibility of false positives is for sure something to consider. But with heart attacks, false negatives are more what we're concerned about, especially you don't want to discharge someone from the hospital or tell them not to pursue further care if they are in fact having a heart attack. So definitely improving the reliability of these tests is definitely something we need to work on. And then Casey asked, increase sensitivity, be able to use less of our sample, ultimately taking less blood fluid. That's the whole goal of microfluidics, is just to use less of a sample so you don't have to require as much blood from a patient or just your overall test equipment requirements. So being able to use smaller amounts of sample, making it a more sensitive test would definitely be beneficial. Dr. Diaz asked, does the concentration of troponin influence the results, or is it just testing the presence of troponin? Also a good question. We would need to, once we get enough reliable tests going, we would be able to, based on the amount of color change, would tell you the amount of troponin present, and then you would just be able to use the amount of blood that you added to the sample to detect the overall concentration, is how I suspect we would do it. That's definitely a long way down the road. We're definitely just getting started with this research. And then Dr. Kolvik asked, could this detect a heart attack before it happens? Currently, I would say probably not. The troponin is only released into the bloodstream after there is damage to the heart muscle itself. So only after the damage has already occurred, but it could detect it earlier before the symptoms become fatal or even more damaging, which would improve patient outcomes overall.
Awesome. Well, thank you very much, Joy.
Awesome. Thank you.
And thanks for sharing your talk with us. That's really cool work.
Thank you.
And then thank you to everyone. That concludes our speakers for this morning. So thanks to everybody for participating in our virtual Student Research Day symposium. And I think it went really well. Thank our judges. Thank you guys for judging. Thank you for presenting. And thank you for just coming in and viewing the presentations. All is greatly appreciated. And hopefully we can do this in person next year.